radioactivity and nuclear physics that we did before. And the final question is question 19. Yeah. And it says, in 2016, there was a breakthrough Starshot initiative. Okay? This project intends to send a fleet of small probes to the nearest star, other than our Sun, Proxima Centauri. This journey would take 20 years, it says. The radiation intensity at Earth from Proxima Centauri is this much, watts per square meter. So that's the intensity. And luminosity is intensity times the sphere that would be enclosing that light at the distance that we're talking about, which is distance to the Sun. And the luminosity of the Sun is given as this symbol L. Can't read it very well because of the photocopy. L this. So that's the luminosity of the Sun. Okay? So that is that value. Okay. They want you to show that, so mathematically show it, how you get it, that the luminosity of Proxima Centauri is about 2,000th of the luminosity of the Sun. Okay, that's what you've got to show. Okay, so the luminosity of Proxima Centauri is the intensity times 4 pi multiplied by the distance from Proxima Centauri to us squared. So you put that value in there and square it. Okay, once you do that, there's the intensity that they gave us up there. 4 pi times the distance squared gives you the basically, if that's the Sun and there's Proxima Centauri, this sphere that goes around the Earth from Proxima Centauri is how much the intensity of light, so this is the Earth, how much it is dimmed. So if it goes from here to this distance, it's now the same power or luminosity is now spread over an area of 4 pi d squared. Okay? So it's obviously less intense. And you get this value, 10 to the 23 watts, 3 significant figures. Then you divide the luminosity of that you calculated by the luminosity of the Sun. You compare them, and you'll see that you get 0.0017, which is 0.002 to 1 significant figure. So you have shown that. Okay? You have managed to show that it's about that. Okay? There you go. To 1 significant figure. So these are all space-based questions, this last run through. The next part says Proxima Centauri is described as a main sequence star. That means it's got to be on this band of stars. Determine whether the surface temperature of Proxima Centauri is consistent with the position of the main sequence of the Hertzsprung-Russell diagram. So it was 10 to the minus 3, so 10 to the... I by mistake, I thought it was 10 to the minus 2, but it's 0.0002, so it's about 10 to the minus 2, slightly above it. So it's going to be over there. So it'll be around there. Make sense? That's a straight line. So it is in the right band of stars, the main sequence, and it's around 3000 Kelvin. Now, let's see. So we got to see if it comes out, what the temperature comes out to. So using the Stefan-Boltzman law, which is this on your formula sheet, where sigma is a constant, A is the area of the star, this time not the distance, 4 pi r squared. Usually when they're talking about the star's radius, they put r, and when they're talking about distance to a star, they put d. Okay? All right, so if you want to work out the temperature, you can change the subject to make t to the 4. The subject is the equation, yes, so it'll be the luminosity that we calculated before, divided by the constant, which is this, the Stefan-Boltzman constant, and then 4 pi r squared. Put in the calculator, you'll get a temperature to the power of 4 of this value. You then need to take a fourth root, yeah, and you'll get a temperature, so to put it to the power of a quarter on your calculator, and you'll get about 3,124. So it's probably this one, because it's slightly more than 3,000. And as you notice, the temperature increases as you go this way on the x-axis. See, over here I got a bit confused and I put 0.002. So be careful in the exam, that should be another 0 in there. 0.002 it should be. Which is why it needs to be drawn approximately there. Okay? 10 to the minus 3. 0.2 times 10 to the minus 3. So if you draw a line and then a line down, it should be around there. Slightly above 3,000 Kelvin. So where our sun is about 6,000 surface temperature. Okay, so we're coming towards the end. Here's part B. Part B says the composition of a star can be determined by the analysis of its absorption spectrum. So this is more on the waves topic. So it looks like for linear students, waves and anything to do with light is the most crucial part of their revision. Explain why there are certain specific frequencies missing from this absorption spectrum. So these are the key words that you must include. Atoms have discrete energy levels. Okay? You need to put that in. Atoms absorb photons of specific frequencies, causing excitation. Yeah? Within the atom, these specific frequencies linked to the absorbed lines on the spectrum cause excitation within the atom. Okay? The energy of photons absorbed, and there's no harm in putting the equation in brackets like I have, equals the exact energies required for an electron to move to a higher energy level. And this is the energy transition which corresponds to the frequency absorbed. Yeah? So it could go from level 1 up to level 2 and absorb the frequency which corresponds to that transition of energy. Okay? So only a fixed number of energy transitions exist in each atom. So only energy, specific energies I should put, again, I should put specific here. Energies of photons corresponding to the frequencies that get absorbed, where F will be equal to the transitional energy between energy levels in the atom divided by H. That will be the frequency of the absorbed photons. And each element has a different set of frequencies which cause excitation. And they correspond to the energy levels. So all existing energy levels. Hope that makes sense. And then you can have a look at the mark scheme to see how many marks you think my answer would get, and then compare it to yours and see if you can improve the clarity of your own written communication. So this is the last part of this exam. Describe how the distance to stars, nearby stars, yeah, obviously Proxima Centauri is the nearest one other than our star, can be measured. For nearby stars, the parallax method is used, whereby a star is viewed from two positions 6 months apart from each side of the sun, and using the diameter of the Earth's orbit around the sun, obviously, allows the change in the angle or position of the star to be measured against the background or the backdrop of fixed stars. Yeah, which are much further away, so like constellations in the background won't move compared to a nearby star. And then 6 months later, they'll appear to have slightly shifted, yeah, depending on your angle that you're viewing from. A bit like a tennis judge, line judge. They used to have them before it was all done by electronic means. If you're not in alignment with something, you can the ball can appear to the left or the right of the line depending on your viewing angle, and that causes uncertainty in your measurement. So this parallax method allows you to measure the angle. So here's the 6 months later, the distance. There's the sun in the middle, and then you look at this star. Yeah, it'll appear again. Say that, but here's the background of stars. So that's the constellation, and you look at it from here. You'll see that it will have shifted from the two viewpoints against the background stars. And if you can then work out the angle it moves, halve it, you can use trigonometry because this will be a right angle triangle, and you know that that's 150 million kilometers or so, the distance from the star to the sun to the earth. So that'll be the sun, earth, earth, 6 months apart. Okay, hope that is clear to you, and that takes you to the final 14 marks of the final question of the paper, worth 90 marks, which is equivalent to the IAL paper. And here is the final mark scheme. Okay. Right, so if you found that useful, have a look at your own answers, see if you can improve your technique by doing so. And you can stop the video if you want to take a longer look at this. Don't forget, once again, show your appreciation, please. Just give a thumbs up. It really helps other students get to see these videos. I think they're good. I get positive feedback from people who've watched quite a few of the videos. Thank you to those people who give positive feedback. And share it with anyone who you know will benefit from watching them. Especially if you know any schools where they're doing the linear one, because I'm now focusing on that because my students have now been entered for linear rather than modular. But really the content is 99% the same. I say 99%, there's a couple of chapters in linear which aren't in the modular. Lenses in year 12 and AC theory in year 13. That's the only difference. Okay, well, here's the diagram that I tried to draw you, which allows you to use the trigonometric method of parallax. Okay, by looking at the star against background, against more distant objects in the sky. Okay, thanks for watching. Hopefully catch you in the next video.